My name is Sharon Liebman. I am the Chief Executive at the ASDC, which is the Association for Science and Discovery Centres, but we don't just represent science and discovery centres, we represent outreach and research institutions and museums, etc., etc. So we're kind of like the largest network of publicly accessible science engagement spaces. And yeah, it's great to see many of you on the call and beyond. I also have Sophie on the call as well. So Sophie is over there, and also Kate, who you'll hear from very soon. Vicky and Scarlett are also here from ASDC. We'll have a chance to meet each other a bit more later on, and always feel free to introduce yourself or say hello to a friend in the chat, and certainly post any questions or comments that just pop into your head during our talks today. I'll start with some bad news, actually. Unfortunately, our wonderful contact at Saxavoord had to be pulled away literally in the last hour or so. So they were going to do a sort of 10-minute spotlight on what is happening at Saxavoord this year. We won't hear from them today, as I say, but we will get back in touch with him down the line and see if they can share a video update, which we can then email all of you. Alongside the other resources, we usually share slide decks from speakers and resources that have been put into the chat. So fingers crossed, we will hear from Saxford in a more virtual update way. So sad to say they can't come, but it was completely unavoidable. We do, however, have our fantastic speakers from ESA and UK Space Agency and NASA here. I'm going to roll ESA and the UK Space Agency into one because Ed Baker is with us from the UK Space Agency and currently at ESA. And he works at the Planetary Defence Office. So Planetary Defence Lead, very cool title, by the way. Planetary Defence Lead at the UK Space Agency. So Ed leads the development of the UK government's first planetary defence capability. He led that in 2024 and is leading the UK government's efforts to join the International Asteroid Warning Network. So when we're talking about planetary defence, you'll be thankful to know we're not talking about anything that's happening right now concerning Trump. We are talking about threats from above. So high on Ed's agenda is promoting planetary defence activities in the UK. So that's why we're lucky enough to have him here with us today. And his session is bound to provide some insights into the national and global planetary defence efforts and future developments. So I might just hand straight over to you, Ed. And as I say, if you've got any questions, drop them in the chat. We'll have time for questions at the end as well. So over to you. Floor is yours.
Thank you very much, Sharon. That was a great introduction. Might have to steal that one for the future. I hope everyone can see my screen okay and my presentation.
Yeah, it's looking perfect.
Great, good stuff. So yes, welcome everyone. So yeah, this is my presentation on planetary defense and how we keep the Earth safe from asteroids. But before we get into the asteroids, we'll go through the really interesting stuff. My background, of course. So just to give a quick introduction as to who I am and how I've ended up in the role that I'm in. So my education, I did my bachelor's at the University of Portsmouth doing geography. I graduated in 2019 and started to work for the UK government in the Department for Business, Energy and Industrial Strategy, or BEIS. And that was doing sort of operations watchkeeper, so kind of keeping abreast of hazards and risks in the energy and business sectors, like COVID, EU exit, various storms, which kind of gave me an introduction into the world of sort of natural hazards to extent, but also how governments respond to them. I then moved over to UK Space Agency, which was kind of the realization of a lifelong dream, where I was working on space response, resilience, and recovery. So again, kind of taking what I was doing at BEIS and then and I'm just doing it with purely space. So I was working on issues such as uncontrolled re-entry of satellites, severe space weather, fragmentations of satellites, but not planetary defense. And that didn't come until a bit later, until I moved again within the UK Space Agency to what is now known as the National Space Operations Centre, or NSPOC, where I started off as a program manager, but during the sort of development of NSPOC, I identified that there was a capability gap with planetary defense. the UK wasn't really doing much on it, and I felt, compare this to what other countries are doing, the US, to what ESA is doing, but even individual countries in Europe, France, Germany, Italy, and even other countries such as China, South Korea, Japan. It seemed like the UK, this was an area which really needed some attention. So I effectively appointed myself as planetary defense lead, and was instrumental in setting up this planetary defense capability, which I'll come on to a bit later, kind of joining the International Asteroid Warning Network, chairing the UK delegation to that network, and also to the Space Mission Planning Advisory Group, or same page. And really just, yeah, as Sharon mentioned, is kind of trying to be an advocate for it with from the perspective of UK government. And pictures on the left, so the top that was a picture taken last month in Vienna. That was a meeting of Same Page. So many countries, and delegations from ESA, NASA are represented here, which was great to see, global cooperation still alive and kicking, especially in the planetary defense community. And then below was a session that I was part of at the UK Space Conference in Manchester last year. Very similar to the presentation I'm going to give today. But what is planetary defense? I think we'll start off with that and give it a clear definition. And really it is the effort to observe, assess, and potentially mitigate or prevent impacts from near-Earth objects, or NEOs, like asteroids and comets, that could endanger Earth. And just to say, a near-Earth asteroid, a near-Earth object, the terms are relatively interchangeable, but it's effectively an asteroid whose trajectory brings it to within 1.3 astronomical units of the Sun, hence 0.3 astronomical units, or 45 million kilometers of Earth's orbit. So it doesn't NEOs don't encompass all the asteroids in the main asteroid belt, only the ones that come very close to Earth orbit, or which intersect Earth's orbit at some point. And this little diagram, which I've put together, kind of helps illustrate that and some of the distances which we're talking about. And just to say, recently we've passed the 40,000 mark of the known NEOs, which is a significant milestone, but as we'll come on to later, doesn't really scratch the surface. And then this is an interesting slide, because I think out of all the space, the risks in space that we kind of associate with space, I think planetary defense is the most characterized, but perhaps maybe also the most misunderstood. So obviously, we all aware of the films Armageddon, Don't Look Up, maybe to a lesser extent Asteroid City, although it explores some of the themes which are relevant to asteroids and planetary defense. Books, TV shows, it really is in the public conscious, and I think part of that stems from, unlike an issue such as uncontrolled re-entry of satellites, that's only an issue that's been has only existed since 1957, since the dawn of the space age. Whereas our association with, and our history with comets and meteorites, especially, dates back thousands of years. So I think there's a human connection, which I'll come on to, but it's also a risk which can be very easily taken out of context, not taken out of context necessarily, but sensationalized, as you see in the various news articles, ranging from BBC, which is quite, very accurate, not trying to kind of overdo it, to the more sort of, this comet is an alien spaceship, which it isn't. I should clarify, it's not an alien spaceship. To the more sort of odd, funny ones, comparing, asteroid sizes to Bono, so it's it's a broad church, and there's a lot as has been written about asteroids and planetary defense. And yes, there is that human experience which I mentioned. My favorite example, and one I often bring up, is the Bayer Tapestry, which on the left you can see. It's the object featured in it is what we now know to be Halley's Comet, which passed by close to the Earth, which does so about every 80 years or so, in 1066, and it was interpreted by the Duke of Normandy as a kind of a positive sign that he should invade England, and it was seen by King Harold II of England. It was for him, it was seen as a bad omen. So again, it really kind of delves into these objects. We've had this kind of connection with them. We've seen them as good or bad omens. They've really formed a part of humanity's mythology dating back many, many years. And even the ancient Egyptian pharaoh Tutankhamun, he had daggers which were made out of metal from meteorites, which again shows that these objects they had quite like even a ceremonial function. It comes from the sky, therefore it must be important, and it's reserved for leaders and things like that. Even in China, these nice little illustrations, which are again Halley's Comet, are just kind of very interesting in how they've depicted it. Even more recently, the Greek composer Vangelis commemorated the ESA Rosetta mission by composing an album, which is actually really good. I recommend you seek it out. But again, it just goes to show how comets and meteorites especially have kind of spurred human creativity and how we've kind of formed this bond with them, I like to think, in a way. But kind of back to the more scientific and aspect of planetary defense. I mentioned in the beginning that planetary defense has three core components: observe, find it, perform follow-up observations on asteroids, assess the danger of them, and then potentially mitigate them. So with the observation, we call them pillars in the community. So in the observation pillar, every night, a global community of space agencies, scientific institutions, and even individuals operate ground-based telescopes to look for asteroids and comets, but as well as to improve our understanding of the asteroids and comets we already know about. The methods used, and I think we'll come on to that, it's all this data is sent to the Minor Planet Center in the US, the MPC, where all the orbits are calculated. But these calculations aren't final because there's small errors in them. They're not always that accurate, which is why we need multiple follow-up observations to refine them. So this is part of the global effort, which goes on every night. And it's not just ground-based observatories. So there's two upcoming space missions, which I'd like to kind of touch on. First is ESA's NEOMER, which is a near-Earth object. I can't remember what the M stands for, but it's in near infrared. So this is going to be looking for asteroids that are currently obscured by the sun's glare. So some of these that we can't see. And this is also what NASA's NEO Surveyor mission will be looking for as well. So the objects which we can't see from the ground because of the sun's glare, we can try and find them in the infrared, and it will really, kind of help discover the ones which are currently just hiding out there a little bit. And just to kind of mention some of the major players in this effort. So I think the Catalina Sky Survey in the US, they average about 350 NEO discoveries per year. And Pan-STARRS survey up to now has discovered 12,000 NEOs, which, as I mentioned from the beginning, we currently know of only 40,000. That's just over a quarter, which is quite impressive. And the ESA NEOMER and NASA NEO Surveyor missions are planned for 2030s and 2027 respectively. So they're missions to look forward to that are coming up. So once we've observed the asteroid, we're kind of calculating its orbit. We then have to assess, is it a threat? So when this data is submitted to the MPC, and what we're looking for is construct its orbit and then model over the next 100 years, is that going to intersect with the Earth? And that's why we need to do continued observation and refinement to really get an accurate number. And the great thing about all this is that it's all publicly available and it's regularly updated. So you can go and see it's NASA's Center for Near-Earth Object Studies, the Century, and then with ESA is the NEO Coordination Center, and they have a risk list of the top 10 current most worrisome risks out there. Just to say, there aren't any significant threats for the next 100 years, which hopefully is reassuring. But my main message here is that it's all available, it's all public, nothing is hidden, nothing is obscured. I think going back to sort of planetary defense in the media and perhaps what people's assumptions sometimes are, whether rightly or wrongly, is that some of this data would perhaps be hidden or not publicly available, and that simply isn't true. And it's not true because that's not the philosophy of NASA, ESA, and the global community. We believe in making it open for everyone to see. And also, we couldn't hide it even if we tried, because there are plenty of amateur astronomers, independent astronomers, who are looking at these objects as well, and will get in touch if they think that we're not making a bigger issue of a certain object. So it is all out there, and it's everyone can see. And then there's the third pillar, and this is the pillar that I work on in my role at ESA. So this is mitigations. So if we discover an asteroid and it crosses the internationally recognized threshold for concern, which for the International Asteroid Warning Network, we call it IWAN, if an asteroid has an impact probability of above 1% and its diameter exceeds 10 meters, then IWAN is responsible for issuing a global alert, which is sent to its members. So, for example, the UK Space Agency, but also the entire United Nations General Assembly. This has happened, and I'll come on to that in a future slide. And that's effectively the role of IWAN, to kind of collect those observations, and then if there is an object which could hit the Earth, then to send out that alert. If the impact probability of an object exceeds 1% and its diameter exceeds 50 meters, the Space Mission Planning Advisory Group, which is comprised solely of space agencies, they get together and they develop a number of mission options for rendezvous, reconnaissance, and/or deflecting the asteroid. And these recommendations are provided to the UN for their consideration and for them hopefully to make a decision. And I should say with IWAN, its members include space agencies, independent observatories, academic institutions, and even individuals. So it's really, IWAN is quite a wide group, open to a lot of different people, whereas Same Page is only open to space agencies. And on the right, you can see these are just some of the methods that we would potentially employ depending on A, the warning time, and B, the size of the object. So you can see sort of civil defense is another area which I'm kind of interested in, and also and then the other kind of mission options, which I'll come to talk about a little bit. But I think civil defense is an area which is being talked about more. It certainly has been by NASA in the last few years, but it could do with some more work. That's speaking from my professional opinion. So how could you deflect an asteroid? And there are a few methods. The one I want to just kind of highlight, and you can see in this very cool GIF, is the one that's already been tested, which is a kinetic impact strategy, which just means smash into it and move it slightly. So this example happened during the DART mission, which was the double asteroid redirection test, where NASA crashed its satellite into the moonlet of an asteroid, as you can see in the GIF, which effectively slowed down its orbit. And that would be a method we would employ, for example, if we discovered an asteroid which was going to hit the Earth in 10 years' time, we could send a kinetic impactor to just give it a little nudge. And then by the time 10 years has passed, the asteroid will be nowhere near Earth. There's other methods such as the ion beam shepherd. So this is firing ions at the asteroid. It's a less destructive method, but it's the same principle of giving it a little bit of a push so it doesn't hit the Earth. Then there's the sort of Hollywood option of using a nuclear explosion. But the purpose of the explosive strategy is not to blow the asteroid apart. It's effectively to ablate one side of it, kind of propelling it. And that option is kind of saved for objects which are A, very large, and B, could hit the Earth in a kind of a short time frame, which required a big deflection. So what is the actual threat to Earth? I've kind of spoken about how we deal with this and how we could deal with this and how it all works. But what the actual threat to Earth is, we're all aware of the asteroid which wiped out the dinosaurs. I'm not going to try and pronounce the name, but effectively this asteroid was, I think about 11 kilometers in size. Those asteroids, the so-called planet killers, we have discovered all of them. So, and they're not going to hit Earth in the foreseeable future, which is good. Um, Even the slightly smaller ones, they're happening at timescales in the tens of thousands or thousands of years. One of the most significant recent ones happened in 1908, was the Tunguska event. This was a meteor which it didn't create an impact crater. It was an airburst, so about 5 kilometers up, it exploded and leveled a number of trees. But because it happened in rural Siberia, no one really knew about it. I think it killed 3 people. Um, and then obviously you have on the other end of the scale the meteorites below sort of 1 meter. They don't really cause any damage. I mean, there was one in Germany a few days ago, and it might break some roof tiles or ruin someone's driveway, but it's not really a big concern for the community. The ones I think we're interested in, I don't want to say worried about, are the sort of, maybe the 10 to 50 meters, and then also maybe the 150 meters. And this is purely because of the damage they could cause. And also, we haven't discovered all of them yet. We're still in this process of looking every night, sending out these space missions to try and find them. So it's still all ongoing. But I think the main message is that there's not a major threat to Earth right now. And in the real world case, so I mentioned, this I1 has responded before, and this happened last year in early 2025 with the asteroid 2024 YR4, which has been in the news recently. Also, I realize I'll come to that, but first of all, so this was discovered in 2024 by the NASA Atlas telescope. It was identified early on as a potential Earth impact threat. And then all throughout January, the impact probability was going up and up before eventually, on January 28th, it exceeded 1%. Therefore, I1 sends out the global alert. Eventually, it peaks at 3.1%. But luckily, through continued observation, because I1 has activated its global community, more observations were able to be made. The impact probability was eventually kind of taken back down to basically 0%. But in the meantime, the UK's response, UK Space Agency / National Space Operations Centre, we issued regular reports to 14 government organisations such as the Cabinet Office. The agency is responsible for civil contingencies for each of the devolved nations. We mobilised our community to try and maybe look at YR4. We represented the UK at meetings of Same Page and I1, and we did a number of social media and kind of news media requests. I was going to say, obviously, there's still a 3.8% chance of YR4 impacting the moon in 2032. We now know that this is 0. That's thanks to JWST, so I must update that slide, which is good news. So now we know it's going to pass safely about 20,000 kilometers from the moon. So all is well, and YR4 can kind of be put to bed for the time being. And this is just an example of what the impact corridor for YR4 could have been if it was going to hit the Earth. So UK wouldn't have been affected directly, but it's still an issue still a global issue, and I think we'll come on to that because I want to kind of go into a what if. What if YR4 had hit London? And effectively, so we're able to look at this through a tool which ESA has developed called the Impact Effects tool. So we can input the characteristics of YR4, what it's made of, how big it is, and see what damage it would cause. And hypothetically, we'll look at what if it was going to hit London. So we can say if it did hit London, then you can see the blue area of the sort of minor injuries. You look at the top here with this scale, the sort of teal color, and it will be a 1 on this hazard diamond here, 1 equating to minor injuries. So minor injuries ranging from Leeds to Paris is, when you say it like that, it is quite scary in a way. And you can see, this is quite a big area that it covers. Looking a bit further in, you can see effectively London is completely destroyed, which is bad news, especially because I live in London. But even in this sort of light green area around it, that's still equating for major hazard to human life. And again, it's quite quite scary to look at in a way. And the hazard diamond is really good for kind of telling you, what the health hazards are, how many survivors you could expect, what's the sort of level of thermal radiation, structural damage, will it be fires, wildfires, buildings collapse, and then an even more zoomed in perspective, in this sort of magenta red area, it's completely gone. I don't have these slides to try and scare people. It's purely for just to kind of show that these objects can cause high levels of destruction. These are low probability, high impact events, and I think government's approaches to those have perhaps in the past not been maybe what they should have. Perhaps COVID was an example of that. But this is just to give you a visual example of the levels of destruction YR4 could have caused if it was going to hit the Earth, and if an object like that hit London or anywhere in the UK. And this kind of goes into a bit more detail about all the different factors you can choose from when you're designing your impact, via the material of the asteroid, a rocky type or metal, the diameter, the velocity, the entry angle. And then in terms of the outputs, you can look at the wind speed, the overpressure, the thermal radiation, and change all these different factors. So you can really make it quite bespoke, and you can go into a lot of granular detail. This tool isn't publicly available. It hasn't really been rolled out to ISAM member states yet. I think the process is ongoing for that. But again, it's good to know that we have these capabilities to do that, and to be able to provide that to member states and to the public, and to first responders. So we've kind of talked a lot about the past, the present, but I kind of want to briefly touch on what the future of planetary defense is. One of the major things I want to talk about is Apophis and the International Year of Planetary Defense and Asteroid Awareness in 2029. So hopefully maybe you're already aware of this, but if not, so on Friday the 13th of April 2029, Apophis, which is a 300-meter size asteroid, will pass very close to Earth at about 31,000 kilometers, which is closer than a lot of geostationary satellites orbit the Earth. It will be visible in the night sky with the naked eye, and it really represents, it's a once in a millennium opportunity, really. And to mark this occasion, the United Nations designated 2029 the International Year of Asteroid Awareness and Planetary Defense. And for this, ESA is planning its mission Ramses to go and study Apophis before its flyby. And the UK is contributing to that mission. And I believe also NASA is planning a mission to go and study Apophis after. And as we'll kind of come on to a bit later, maybe there's opportunities for people in this group to get involved in that as well. So I forgot to change the title of this slide, but this is basically the UK approach. So I've spoken a lot about what the kind of global community does, but to speak a bit more about what the UK does. So I've mentioned the planetary defense capability is managed by the National Space Operations Centre. Effectively, we're responsible for taking receipt of notifications from IWAN, same page, and distributing them across across UK government, being that sort of trusted expertise on asteroids and planetary defense. Attending international meetings of same page, IWAN, ESA, NASA as well, and really kind of acting as the face of planetary defense in the UK. We were a founding member of Same Page in 2013, and we joined IWAN in 2025. We actually joined IWAN 5 days before the global alert for 2024 YR4 was issued, which was a bit of good timing on my part. And as I mentioned, through ESA, we're contributing to the Ramses mission to Apophis, but also the Fly-Eye telescope, which I'll talk about in the next slide. And we're also a co-signatory of the International Year of Asteroid Awareness and Planetary Defense through the United Nations. And we operate on a number of telescopes and observational facilities, which primarily do sort of satellite tracking, but can also track asteroids if we ask them to. And this example here is Chilbolton in the south of the UK, which is quite nice and picturesque. And I think the reason I've saved this slide for one of the last ones, I think it's the message I really want to get home is the nature of planetary defense is changing. And the big occasion on the horizon, which I think everyone needs to be aware of, is the Vera Rubin Observatory. So, I mentioned in the beginning, we know of 40,000 asteroids already. Sorry, 40,000 NEOs. And that is what we've discovered between 2026 and 1801, when the first asteroid was discovered. So that's covering, 227 years. The Vera Rubin Observatory in Chile, over the next 10 years, is expected to help increase the number of discovered NEOs from 40,000 to 127,000. And in June 2025 alone, when it was going through its sort of initial testing and operational phase, it discovered 2,000 new asteroids in the solar system. So some in the main asteroid belt, some of the trans-Neptunian objects, as well as 7 new NEOs. So events like 2024 YR4 are going to become more common. Maybe there's going to be an asteroid which isn't going to miss the Earth and is going to hit the Earth. These events are going to become more frequent, and I think it's important for governments around the world, including the UK, to take the risk more seriously, but also people in the community to be more aware, the general public to be more aware about the changing nature of planetary defense. And I think Vera Rubin will really change that. These missions, NEOMIR, NEO-Surveyor, are all going to change it. Again, none of this is meant to scare people. It's always just kind of, to be honest and upfront that the nature of the risk is changing. And ESA's FLY telescope, which will be operational this year, it's based in Italy. Again, it's going to be looking at searching the sky every night for new asteroids. So, there will be more events like YR4. So it's kind of a case of watching the space for them, and being prepared for them. And in terms, also future space missions, I've spoken about OSIRIS-REx and Ramses as well. So I won't cover this too much, but there's also the scientific value of studying these objects. So Japanese Space Agency's Hayabusa 2 in 2014, taking samples from asteroids. There's an upcoming mission from the Chinese National Space Agency, which is also going to be getting some asteroid sample returns. So I think that's why 2029 is the International Year of Asteroid Awareness and Planetary Defense. The asteroid awareness side, these are also objects of great scientific value. They offer an insight into what are effectively the building blocks of our solar system. These objects which have remained relatively unchanged since the formation of the solar system. So they're objects of both sort of fascination and fear. So it's not just to be fearful of them. It's also to try and understand them and to learn more about them and learn more about ourselves as a result. And I think hopefully you're interested. Hopefully you love planetary defense now, and you wanna do more. And this is why I have this slide here: how you can get involved. So I've spoken to death about the International Year of Asteroid Awareness and Planetary Defense. The UN is hoping it will be facilitating a number of activities, but they're also encouraging member states to run their own programs. So, maybe this is a message for all of you to kind of lobby the UK Space Agency to do some events so that they can ask me to lead them and coordinate them. A joke, but but also in terms of running your own activities, your own programs. I'm sure that, this association will be heavily involved in that. So, plan your activity, get it officially badged by the UN, I think will be an option. In the meantime, every year, June 30th is Asteroid Day. So this is recognized by the UN. Again, they're coordinating a number of activities, mostly I think they're based in Luxembourg, but these activities go on all over the world. So try and find an event, maybe schedule your own event to get people involved. I think, turnout for these events is always really high. And then more practically, on the sort of, is joining I1. As I mentioned, it's open to effectively anyone who has access to observational capabilities, skilled amateurs to independent observatories. You can search I1 how to join and read about the sort of admission requirements and the process for it. But if you have access or you know someone who does and you think they'll be interested, then I encourage you to go and do it. And I think, this my presentation, but please do connect with me on LinkedIn or email me if you have any questions about the application process, how to join, or just any questions in general from this presentation. Happy to answer any. Hope you've enjoyed it. Happy to take questions, I think, maybe a bit later. But no, just thank you for your time. Appreciate it. Thank you.
Yeah, so I'm not going to do the demo, but I'm going to introduce Ellie McDonald, the Science Engagement Lead from Kildare Observatory. They've got a couple of brilliant activities they want to share on meteorites. So over to you, Ellie.
Yes.
Thank you.
I will try to share the correct screen because there are a million things open. But I think this should be right for now. So can everyone see this?
Yeah, it's looking great.
Yes, lovely. So yeah, thank you for inviting us to come and talk today. Basically, we just wanted to share some of the meteorite workshops that we do at Kildare Observatory because there's something we've done since the beginning, and every single event we run, the feedback we get is that people enjoy the meteorites workshops more than pretty much anything else. Even on clear nights, we have people who want to look at meteorites instead of look at stars sometimes. And so we thought we'd share what we do at the observatory with the meteorites themselves, but also the workshops that we've developed for when we can't necessarily take those out. So at the observatory, the sort of general workshop we do is pretty straightforward. It's a matter of explaining to people what meteorites are, what meteors are, and also what asteroids are as well. We tend to field lots of questions about things like, are asteroids going to hit the Earth anytime soon? And it's a really good time to have those conversations with people. But the highlight is always, getting hands-on with them. So we have a collection of meteorites, a collection that we both take out into schools and also a collection that we have at the observatory. I think the school's meteorites are probably some of the most well-traveled meteorites on Earth at this point. I would love to actually at some point try and figure out how far they've traveled on this planet in total. But here you can see a picture of Adam showing some people just our collection. And this is great, wonderful. But as I mentioned, we're not necessarily always able to do this. So over the last couple of years, we've been involved with a couple of different projects where, for example, we've been working remotely with really large groups of people, and it's just not really feasible for us to send every school, a collection of meteorites all to have a look at. We had to figure out other things that we could do. And so we started to think, well, maybe they could kind of make their own meteorites or get thinking about how to make their own meteorites. And so we kind of changed the way we presented things, and we looked at more features on the surfaces of meteorites that people might notice. So we highlighted one feature, which is regmaglyphs that you get on meteorites quite regularly, which are these kind of like, it looks like someone's taken clay and just squashed it basically and started like pushing their fingers into wet clay. And that was kind of the inspiration for what the workshop ended up becoming. But we did also mention fusion crust to people. So we were highlighting these like two different features that we commonly see. And as you might have guessed it, for the workshop we did with schools at least, we gave them all some lumps of clay. And I did consider going down to the lockup and grabbing some clay to make your meteorite today, but it's quite a messy workshop. I will warn you if you want to do it. But it's fun. The kids definitely enjoy it. And you can see that we've got pictures of them here molding the meteorites. We gave them a couple of tools to work with. And here are some finished products. Definitely got some regmaglyphs in there. I'm not too sure about fusion crusts. But this is it's a workshop that we did with schools for a couple of different like after school programs that we were running. But we did also take it out to festivals a couple of years ago, which was even messier. as I'm sure you can imagine. So this is from the Deershed Festival, which is in Yorkshire. And I don't necessarily know if the kids at all made meteorites with this one necessarily. I think they all just took creative liberties with the clay they were given. But some of them were looking at least a little bit lumpy. So that's kind of one alternative workshop we do around meteorites when we can't necessarily give people rocks themselves. The other thing that we started doing though, and this is something that I've been excited about for a while, is we started to think, well, can we help people find their own meteorites? You've got these rocks coming through the atmosphere, they break up, they get turned into dust. And so we for ages wanted to try hunting for micrometeorites, and we got a really good opportunity to do this through the Explore Your Universe project that we were running, and we were running this with the West End Refugee Service. So when we were doing our co-planning workshop, we gave them a bunch of different themes, one of which was about asteroids and planetary defense. And I mentioned micrometeorites offhandedly, and the entire group just ran with it. They were really excited about the idea of finding micrometeorites. So that's kind of where this other thing came from. It was about thinking about the stuff that rains down to the ground and how we can go looking for it. So if you're not aware, the Earth gets loads of micrometeorites falling towards the surface every single year. So it's around about 5,000 tons of micrometeorites that we get, which is around about the same as not one, but two Eiffel Towers. And because it's falling everywhere, you've got as much chance of finding it in one place as the next. But if you have a flat rooftop, you're in a bit of luck because that's where you're most likely to find stuff gathering and undisturbed. So this workshop started off with me climbing onto the rooftop and sweeping it for the first time in about 3 years. And then once I'd swept it, there was kind of like a procedure that we had to go through. Now, the procedure, I looked at a couple of different sources to figure it out. So one place that I looked is I had a little look at this website called micrometeorites.com, which just is a really lovely set of information if you want to do something like this. The Sky at Night also has a little how-to guide now, and something that is blocked in here that I was hoping I'd be able to show you is, of course, there is the book by John Larson, all about meteorites, but that is being blocked by the Sky at Night right now, unfortunately. So the book and the websites are sort of the guides that we took for this. But in essence, we knew that we were looking for something like this. We were looking for like these little globules. Now, micrometeorites don't necessarily always look like this. They're not always round. They're not always like metal either. You do get quite diverse micrometeorites, but for the sake of simplicity, we just decided to tell people, we told our group with the West End Refugee Service that we were looking for the round metal ones because that's just easier. And as I said, the procedure that we sort of developed was you get a magnet and you put it in a bag. Then you get the dirt that I'd gotten off of the roof and you take all of the dirt that was magnetic and you wash it. Once you've washed it, you give it a day or two to dry out and you go through it with the magnet in a bag again and you pick up all the metallic stuff. Now, you can repeat this sort of washing step a couple of times. From what I understand, it does help it a little bit, but we just repeated it once or twice. Then you need to sieve it. And for a micrometeorite, you're usually only looking for things that are 4 millimeters and under. So that's the type of mesh we used. To find mesh like that, I literally went onto a website that sells purely mesh and I got a sample sheet and it was fairly cheap that way. And then it comes to looking underneath a microscope for it. So this is actually a picture of a microscope that I think we ended up buying. So it's very low quality because it's just like an Amazon listing. But we gave it a go and we did find some fairly small little woolly things. And I'm hoping this will work out as well. I can change hopefully the screen that I'm sharing. And I'll check that it's going to be the right one. Yeah. So hopefully now you are seeing an actual live view of the rock that we were looking at. So this is from my phone and hopefully like me, you can also just about see that there is a little round thing there. But basically, looking underneath the microscope, it's basically a case of you just pushing stuff around And as you're pushing stuff around, you're just sort of focusing and unfocusing. And there's something quite calming about it. There's something quite distracting. You end up spending hours on it. But people seem to really engage. I'm also aware that there is a way to do this a lot more efficiently, where you're sort of using less dirt and you're going through it one at a time. But I don't ever particularly have the patience for that. So I just work with plastic, like pushing loads of mass of dirt around. And even if you don't find micrometeorites, it's actually just really interesting to see what falls on your roof over time and what gathers. And so there we are. It's a very quick little bit of information.
Brilliant. Thank you, Ellie. That was really interesting. Great. Is there any questions? Otherwise, we're going to be moving on. But yeah, thank you again for that demonstration. The wonders that are on Kildare Observatory's roof. Okay, brilliant. So I'm going to introduce our next speaker. That's Raissa, who is a researcher at NASA's Jet Propulsion Laboratory in California. So she's got up quite early to join us today. She holds a degree in physics from the Federal University of Rio Grande do Norte in Brazil, and has a master's and doctorate in geospatial sciences from Mackenzie Presbyterian University in Sao Paulo, Brazil. Her doctoral thesis was on exoplanets, atmospheres and habitability, and was awarded as the best thesis of 2020 by the International Astronomical Union. Currently, Raissa works on the characterization of planets beyond our solar system and serves on the Science Committee for NASA's Habitable Worlds Observatory, a flagship mission designed to search for signs of life and Earth-like planets. So she is going to join us now and tell us a bit more about that mission. So hand over to you, Raissa. Thanks for joining us.
Thank you. Thank you very much for the invitation. Thank you for the introduction. Let me start sharing my screen. Thank you. Sorry for this.
No problem.
Okay. All right. Let's start. All right. Thank you again for the invitation, for the introduction. My name is Estrela. I'm a research scientist at NASA Jet Propulsion Laboratory in Pasadena, California. And currently, I serve as the co-leader of the scientific engagement of the Habitable Worlds Observatory, together with Rob Zallan, who is in the call. The Habitable Worlds Observatory is a mission, a NASA mission, is specifically designed to search for life beyond our solar system. And I'm very excited to tell you more about this mission today. But before we dive into the science and the details of this mission, I would like to give you like to share with you a little bit about my journey to become a NASA scientist working with this observatory. So my entire career has been driven by this one simple question: are we alone? And it's a question that has been born by the restless curiosity imprinted in our human DNA. When we look into the stars, we wonder if there is someone or something out there, right? So having this question in mind, I started my career in this little city on the coast of Brazil. It's called João Pessoa. As you can see, there is a beautiful Atlantic Ocean surrounding the city. And I was very lucky because right next to my home, there was a planetarium. And that was my first contact with astronomy. But back in the early 2000s, I was also very concerned about the climate emergency that we were facing. And that led me to actually move to a town 2 hours north away from my hometown to another town called Natal to study ecology. So although I had this first contact with astronomy and I was interested about that, I actually moved to study ecology. But during my undergrad studies in ecology in Natal, NASA launched the Kepler Space Telescope. And that mission fundamentally revolutionized astronomy by discovering thousands of planets outside of the solar system. And inspired by this mission, I left a note under the door of a professor of astrophysics at my university. And to my delight, he responded and he invited me to join his team. And I began working with the Kepler data to understand the diverse stars that serve as sun to another planets that were being discovered by the Kepler mission. So Kepler in that time actually discovered more than 2,600 planets. And by now, we know that there are more than 6,000 exoplanets detected. So during that time, in Natal, I decided to move to physics. So I left my ecology degree. I went to physics. I continued studying, working with the Kepler data. And I moved to São Paulo in the southeast of Brazil to start doing my master thesis. And there I focused on the magnetic behavior of stars that are stars detected by Kepler that were hosting planets. And I continued in the same institution to do my PhD, where I shifted a little bit my focus to study the planets themselves, and specifically how the magnetic behavior of these stars would impact the habitability of the planets. But during that time in my PhD in São Paulo, I wanted to answer, do these planets have an atmosphere? And if they do, what are these atmospheres made of? Could we eventually find signs of life within these atmospheres? So motivated by these questions, in the second year of my PhD, I moved from São Paulo, I moved from Brazil with my 3 cats to start an internship at the Jet Propulsion Laboratory, where I am today, to study the atmosphere of these exoplanets using the Hubble Space Telescope. So during that time, during my internship at JPL, I used the Hubble data and I found evidence of a planet with the same size as our planet that have an atmosphere that was lost, and this planet was gaining a secondary atmosphere, which is a process that we also believe it happened with our own planet. So after my internship at JPL, I became a postdoctoral fellow, and last year I became a research scientist at JPL. When I say JPL, I mean Jet Propulsion Laboratory. Just to give you a taste of the things that I saw during this time at JPL, the first year I had the privilege to see the Perseverance rover, which is a rover that was sent to Mars. It was built to seek signs of ancient life and collect samples of rocks in Mars. So in the left image that you see here, you see the Perseverance rover being built and the JPL clean room. So that is a picture that I took in that time before 2020. On the right, you see me and my friend, we were watching the landing of another rover that was sent to Mars, the InSight rover, in 2018. And the bottom picture, you see the first picture that was taken by the Perseverance rover when it arrived in Mars in 2021. And later, I had also the privilege to see other rovers being built at JPL. So on the left, you see the Europa Clipper. Europa Clipper is a solar-powered spacecraft that was built to conduct the first detailed investigations of Jupiter's ice moon, Europa. So right now, Europa Clipper is actually traveling on the space 1.8 million miles to arrive to reach Jupiter in April 2030. And on the right image here, you see me in the mission control room at JPL, which they control all these missions that are out in space. But back to my research, so far in my career, I have not yet been able to answer the question that first drew me to astrophysics: are we alone? But that may change because in the coming decades, because in 2020, the Astrophysics Decadal Survey, which is a panel composed by experts, they set the scientific priorities for the next decade. And they recommended this observatory, the Habitable Worlds Observatory, which is a future NASA flagship mission designed to search for the signs of life outside of the solar system. So it's the first mission designed to search for life outside of the solar system. HWO will be like a Hubble 2.0, will be larger, it will have a larger mirror, and it's going to have the ability to observe planets in 3 colors of light, 3 colors that are very important to detect forms of life. One is the ultraviolet, the other one is the visible, and the near infrared. So together, these three colors of light, they provide the necessary data for us to scan both the atmosphere and the surface of planets that are outside of the solar system. But how will Habitable Worlds Observatory search for life? What is the technology behind it? How can we detect signs of life? So let's take as an example this image, which is a simulation of like a practice run for the Habitable Worlds Observatory. And this image shows how our solar system would look like if a telescope like HWO would be sitting light of years away from us. So if you notice the black void right in the center of the image, that's the most important part of the technology of the Habitable Worlds Observatory. To see a planet, we need to block the light that's coming from the star. So we can use this technology that we call the coronagraph to block this starlight. So it's like we're creating an artificial eclipse to hide the star, so we can see the faint glows that are coming from the planets around it. So the planets are finally emerging from the shadows. So once the star is blocked with the coronagraph, we can see this light that's reflected by the planets. So on the left, you see here Jupiter, which is a bright, big spot that's easy to spot. You also see Saturn. So these two are the giant planets in our solar system. But if we go back to the center, right inside of the red glow that we're seeing here, we see two other tiny dots. And these other tiny pixelated dots are Venus and Earth. So to an alien telescope, basically our entire world, our entire planet, with our oceans, with our mountains and history, everything will be just this single pixel, lonely pixel of light. By taking that tiny bit, that tiny pixel of light and spreading it in a rainbow, we can look for the fingerprints of light. So HWO, the Habitable Worlds Observatory, will have an instrument called a spectrometer. You can think it like a prism. If you're familiar with the iconic image from the Dark Side of the Moon from Pink Floyd, it's basically the same that you're seeing here. It's like a prism that HWO is going to be collecting the white light from the other stars. And this prism is able to collect the light and break the light in different colors that the scientists call wavelengths. So when the light interacts with a planetary atmosphere, molecules, they leave behind fingerprints. They leave a spectral a fingerprint, their signature in that light. So in the ultraviolet, we can look for these specific fingerprints from gases. In the optical, oxygen. In the near infrared, we can see the fingerprints of methane. All of those which are related to life in our planet. So going back to our simulation of the solar system, here on the left, if we take the tiny light from our planet, that reflected light, and we spread that in different colors, we can see the fingerprints of the molecules in our atmosphere. So the horizontal axis here on this graph is basically giving us the different colors, right? So the left, we see the ultraviolet and blue colors of light, which our eyes can see. But as we go to the right, we are going to the near infrared. So it's a light that's beyond what we can see, right? But each of these light contains a fingerprint of what is in our atmosphere. So if you look in the blue, for example, we can see what we call Rayleigh scattering. So that is the physical signature of a thick atmosphere. It's the reason our sky is blue, right? It's the reason everything is blue right now for me. I'm daylight still here. So if we look in a planet that's distant also, and if we saw the same signature in the blue, we would know that that planet has a thick atmosphere. Maybe their sky is blue. If we go to other colors, so if we move more here into this blue part of the color, we can also see oxygen. And the ultraviolet, we can see ozone. So both molecules which are related to life. Oxygen is a product of photosynthesis from vegetation, and the ozone is also a subproduct of that. If we move to the near infrared, we can see signs of water and also of carbon dioxide and also methane. And methane is also related to life in our planet. It can also come from the fat from the cows. But Habitable Observatory will do far more than search for life. It will be a powerful observatory telescope for addressing many fundamental questions in astrophysics. We can seek with HWO, we can seek answer for many questions. For example, how many black holes are in the Milky Way? How do stars and planets form? What is the nature of dark matter? What are the characteristics of near-Earth asteroids? How do most massive stars live and die? So there are many other astrophysics questions that this observatory will be able to answer. And also, HWO will offer us two profound possibilities as well. If we find signs of life, it will reveal that planets like Earth are extremely rare. This will show us that our world is even more precious and fragile than we already know. But if HWO detects signs of life in another planet, it will also fundamentally change our understanding and our place in the universe. In either case, it will give us a perspective. The cosmos is reminding us just how small and delicate our planet truly is. So by studying these distant suns, the Habitable Observatory will offer us a humbling perspective of our planet, much like the Voyager 1 spacecraft did back in the days, in the 70s, when it turned the camera and looked back towards our home to make one final family portrait before leaving the solar system. The image that you see here in this slide is that final look back. In it, Earth appears as a tiny solitary dot suspended in a sunbeam. It was an image that was inspired the late astronomer Carl Sagan to call our home the pale blue dot, a pale tiny dot, rocky, floating in a sunbeam. But we inhabitants of that tiny dot, we know that our pale blue dot is actually not that so pale. It's actually a colorful composition of biodiversity and other life forms. So I would like to finalize this short presentation to leave you with this reflection from Carl Sagan, which is inspired by the image of our tiny planet, with a reminder of the responsibility that we share to care for this tiny world and all of its inhabitants. So by looking to that image of our planet in the same way that we are going to be looking to other planets with the Habitable Observatory, I would like to give you this perspective from Carl Sagan. He said in his book, The Pale Blue Dot, there is perhaps no better demonstration of the folly of human concepts than this distant image of our tiny world. To me, it underscores our responsibility to deal more kindly with one another and to preserve and cherish the pale blue dot, the only home we ever know. So I would like to leave you with some information here. That's the image of our first Habitable Observatory conference last year in Washington, D.C. It's a big team, as you can see. And also, if you are more interested in more information, updates from the mission, subscribe to the mail list, you can scan this barcode here. And I'm open for questions. Thank you.